After integrating out the high energy mode for a system of cold atoms, we ended up with a Lagrangian for a massless Goldstone mode. We can rescale the field to end up with a more familiar form for this Lagrangian. This Lagrangian exhibits similarities with the Klein-Gordon Lagrangian for a massless field. If we restore C and H bar, and if we plug in this Lagrangian into Euler-Lagrange equation, we see that we get a wave equation with the speed of the wave equal to c. And the corresponding particle has an energy, which for a massless field, by analogy we see that our effective Lagrangian for the Goldstone mode describes a massless field, which in the classical limit gives a wave equation with a velocity, and thus an energy. This equation relating the energy with the momentum is called a dispersion relation. Usually for a non-relativistic field, the dispersion relation gives us an energy which is quadratic with the momentum. But now for cold atom with a repulsion, spontaneous symmetry breaking gives us a dispersion relation which gives an energy which is linear with the momentum. This difference is what explains the superfluid behavior. Superfluidity is characterized by the motion of a fluid which is without any viscosity. And viscosity is produced by the collision of the particles in the fluid, which lead to a dissipation of the collective kinetic energy into internal heat, internal excitations. If we consider a normal non-relativistic field with an energy which is quadratic with the momentum, because of the finite volume we have a discretized set of momenta. We see that at low energy there is a lot of possible available states to the particles. This large level density at low energy makes a collision very effective to dissipate collective energy into internal excitations. However, in the case of a superfluid, we have an energy which is linear in momentum. This strongly reduces the number of available states for the system. As a result, when two particles collide, they are not as likely to find an available final state to populate. Therefore, this makes the collision less efficient, and as a result, that reduces dissipation and produces superfluidity. Manifestations of superfluidity are quite remarkable, with superfluid going through the bottom of a bucket or climbing up its edges to escape.